Hello.
All right, great. Thanks so much, Karen. Yes, I'm pro solar, and it was awesome to see more arrays pop up in the years since. Yeah, so hi everybody. My name is Patrick Walsh. Some of you might know me from the coffee shop days, but my area of my career is in advanced technology vehicles. So let me just see if I can pull up the slides here. Let's see, share screen. I think David might need to give me access first.
Yeah, I'll just make you the host.
Okay.
Okay.
Okay. We'll share this. Okay. It looks like I am unmuted. Am I unmuted, Dave? You can just nod.
Yes, yes.
Yeah,
yes.
okay. Okay, cool.
Yes, I hear you.
We'll go full screen. Okay, so hi everybody. My name is Patrick Walsh. I am a consultant with Argonne National Laboratory. For those of you who don't know, Argonne is one of about a dozen or so national laboratories scattered around the country under the wider umbrella of the Department of Energy. And I've been working in this field for about 11 years or so in various capacities. And so today I'm going to talk about the topic of well-to-wheel impact of vehicle operation. In doing so, I'll cover energy use, greenhouse gas emissions, and environmental pollution. And I also added some pretty good references and additional resources at the end that you can go look at on your own in case you find those useful too. Okay, so let's jump right in. So first I'm going to start with a sort of a basic introduction to this topic with some definitions of what we'll be talking about. And then we'll look at the energy use component, energy sources, and the use of energy, followed by the environmental pollution component. From there, we'll take a look at greenhouse gas emissions before getting into a helpful example or two to help illustrate all of this. And hopefully there'll be some time at the end for questions, and I can point you, as I said, in the direction of some pretty helpful resources and references that I used to make this presentation. Okay, so why does this matter? Let's start with the big picture look at why we're talking about all this. If we want to understand why we study the impact of vehicles, let's first understand how much we are driving those vehicles. And to do so, let's define a very simple term called vehicle miles traveled, VMT. That's effectively all the miles traveled by all the cars in the United States any given year. So this plot from the Department of Transportation, specifically the Federal Highway Administration, shows over time from 1970 to basically the present, just how much more we've been driving every year. It's been a 286% increase since 1970. And I think this plot is current as of about 2018 or so. So that's a huge increase, but also it's important to look at on the vertical axis, those units are millions of miles. So in 2017, there were 3 trillion miles traveled by all the cars in the United States. So that's quite significant. And as our vehicles are driven more, the negative impacts of operating those vehicles, they become more significant and they have to be mitigated. So let's look at what are the impacts of all that driving and how does industry, government, academia, how are they working to mitigate those effects? So starting with air and water pollution. in order to produce and drive a vehicle, various processes along the life cycle negatively impact air quality and water quality, which is a problem for humans and animals. Air pollution is of particular concern in densely populated areas such as large cities, and water pollution can result in toxic compounds getting into the water, getting into the fish that we later eat, impacting biodiversity, just as an example. Then there's greenhouse gas emissions. Carbon dioxide, which is a greenhouse gas emission, is released at various stages of the vehicle life cycle, production, driving, and that results in significant contributions to climate change. And I won't touch on the details of climate change factors in this presentation, but we will look at the contribution of the vehicle itself towards climate change. And then there's the economics of affordable transportation. Since our economy is heavily reliant on affordable transportation of people and goods, vehicle energy efficiency is important to consumers as well as to businesses and municipalities. There's also long-term sustainable energy sources for transportation. So this plays into our quality of life, our way of life. And someday, fossil fuels will eventually run out, and we will have to move to sustainable sources of energy to maintain our quality of life, our way of life, in the long run. So petroleum-powered vehicles, gasoline-powered vehicles will eventually be phased out due to lack of resources. And finally, there is a national security, a global security aspect to this. It's a fundamental interest of our country and also a mission of Department of Energy to become as energy independent as possible, meaning we as a country rely less and less on other nations for our own energy supply. This gives our country a more secure supply of energy and promotes security for our nation and the stability in our economy. So those are the overall impacts. So another definition that is important to address is what do we mean by well to wheels? That's in the title of the presentation. So what is well to wheels? What do we mean by that? So let's start with the well. What is the well? The well is the source of energy that will eventually be used to propel the vehicle. And it's also referred to as the feedstock. So we're going to pull up this little chain here to illustrate. This feedstock, highlighted in red here, it could be crude oil, it could be natural gas, it could be radiation from the sun, to give a few examples. From there, the feedstock is transported to a place where it can be then refined into usable energy for a vehicle. From there, the refined fuel can be transported to a distribution point, such as a gas station or charging station, and then dispensed to the vehicle at the pump or at the plug, if you're talking about an electric car. And from there, we arrive at the vehicle itself. This is called either the tank to wheels portion or pump to wheels. It's a little bit interchangeable, but this is the vehicle itself. So operating a vehicle constitutes sort of two main areas to consider, from the well to the pump, which is considered the upstream component, and then from the pump to the wheels or the tank to the wheels, which is considered the downstream component. Upstream takes into account raw energy extraction, refining, distribution, and transportation. And then downstream takes into account the energy efficiency of the vehicle and whether the vehicle itself produces any emissions. So well to wheels takes into account the entire process, where the fuel came from, how it got to the vehicle, and then how the vehicle uses that fuel. So that's well to wheels. So where is this energy coming from then, typically? Well, energy has to come from somewhere to propel a vehicle. So let's look at some traditional sources and some renewable resources. Traditional resources are essentially relegated to raw petroleum, which is refined into gasoline or diesel for on-road vehicle applications. The benefits of a traditional petroleum-based pathway are cheap fuel for consumers and businesses, even though that is significantly subsidized, a well-established fueling infrastructure, with conveniently located gas stations all over the country that enable quick refueling, refining methods that have become very efficient over time, the high energy density of gasoline or diesel fuel itself, which allows vehicles to store enough energy on board to travel very long distances. And we're also able to source some petroleum domestically. But the drawbacks of this traditional pathway include significant carbon and air and water pollution resulting from both upstream and downstream components. The feedstock itself is non-renewable. There are many complicated factors involved in the importation of oil, and the price of oil can be unstable depending on global markets, which are beyond our control. So it's also important to, well, first let's look at some alternative resources. So these are the traditional resources. So what are the alternative resources? Well, a few mainstream examples include grid electricity, natural gas, hydrogen, and biofuels. The benefits of these include reduced carbon and air pollution emissions. They are renewable, except natural gas, which is not. All can be sourced domestically, and there's potential for really significant improvements in energy efficiency from well to wheels and long-term operating costs. The drawbacks of these pathways are the distribution infrastructure is still limited, but is significantly improving. The upfront expense of vehicles that are powered by renewables can be prohibitive to some, but gradually over time, that upfront expense is getting lower and lower when compared to a traditional vehicle. And the electric grid itself can be dirty in some areas. So the electricity could come from coal, it could come from nuclear, it could come from renewables. So the grid can be dirty, but the grid is always improving, as we'll look at in a bit. So those are some alternative resources. With all of these factors in mind, it's worth noting that the Department of Energy's mission includes improving nationwide vehicle energy efficiency, moving towards sustainable sources of energy, and reducing the need for imported fuel. So those are some key missions for the Department of Energy. So energy, let's look at energy usage for vehicles. So according to the National Academies of Science, the United States uses 28% of its total energy each year to move people and goods from one place to another. So improving the efficiency of the upstream and downstream components of transportation is important for our energy security, our economy, ultimately our environment. So where's one area that we can start? Well, improve the vehicle itself, improve the vehicle efficiency. So this diagram is going to show where the fuel energy that you put into a conventional vehicle goes over the course of driving it in typical city driving. So 100% starts at the fuel tank, the fuel going into the vehicle. So where does this energy go as you drive the vehicle? And this is based on, sort of standard EPA tests that every single car that's put into production is run on in a laboratory setting, city driving, the federal test procedure. So where's this energy going? Well, right off the bat, 62% is lost to heat because of the engine. The heat goes out the exhaust, the heat goes into the coolant circulating through the engine, and much of that then goes out to ambient air through the radiator. So the engine itself loses quite a bit of that fuel to just pure heat. Another 16% is lost to just engine mechanical losses, the engine doing its thing, pumping, drawing in air, overcoming friction, operating accessories, fuel pumps, oil pumps, power steering pumps, that sort of thing. So just the engine doing its thing is another 16% gone. Another 10% is gone to the drivetrain. So the transmission, the differential, the wheel bearings, any braking that you have to do, that wastes energy in a conventional vehicle anytime you're idling. So what are we left with to drive the vehicle at the wheels? 12%. And that energy is used to overcome inertia to get the vehicle rolling, It's used to overcome rolling resistance of the tires, air resistance. The faster you go, the higher the air resistance, and overcome gravity if you're climbing a grade. So, big picture, we started at 100% fuel, and the vehicle system itself is 12% efficient at converting gasoline into motion, basically. And this information is a little dated. I reran these numbers more recently, and that number is closer to 18% for conventional vehicles. So it has improved since this was created about 7 years ago, but it's still pretty bad. So let's compare this to an electric vehicle. So this is a conventional vehicle. Let's look at an electric vehicle. So electric vehicles are considerably more efficient at converting their onboard energy to driving motion. So we'll bring up another diagram that will show the energy going into the vehicle from the battery. So there's no fuel tank, it's the battery. And where does that energy go to drive the vehicle? Well, the big blue triangle there is 100% battery energy going into this Nissan Leaf. And this is all data that was generated at Argonne, the test facility there. So over this standard city driving, just like the other vehicle, 73% of that is going to the wheels to drive the vehicle. Only 22% is lost to the powertrain, and about 4% is lost to accessory loads like air conditioning, power steering, that sort of thing. So an electric vehicle powertrain is much more efficient at converting the fuel that you put into it to actual motion. It's also important to consider, though, that there are efficiencies associated with generating that electricity. So where does that electricity come from? Well, it could come from coal, which is about 33% efficient, a coal-fired power plant at converting coal to refined electricity, AC electricity. Petroleum is about 31%, natural gas 44%, nuclear 33%. So some efficiency is traded off upstream in the generation of electricity in order to have a very efficient vehicle downstream. So what we need to do is then compare the well to wheels, the whole big picture energy use of gasoline and electric cars to get the full understanding. And I'll do that in a little bit. But first, let's move on from energy to environmental pollution. So when combustion, the process of combustion is used to generate usable energy, some toxic compounds are created and released into the air and into the water. These toxic compounds are harmful to humans and animals. They could be called toxic compounds or pollutants. And conventional combustion engine vehicles emit these toxic pollutants that are regulated by the EPA. Nitrogen oxides, or NOx, these cause respiratory concerns. Unburned hydrocarbons, these cause smog, also respiratory concerns. Carbon monoxide, which is toxic to humans. Particulate matter, which is very, very small particles that can get in your lungs and are really nasty for respiratory concerns. Formaldehyde also causes respiratory concerns, and this is part of like a catch-all group called NMOG, non-methane organic gases. So these are the pollutants that are being regulated, and the EPA has worked with auto manufacturers since the early 70s, the Clean Air Act of 1970, to reduce harmful emissions from vehicles. So how successful has that been? Well, vehicle pollution control under the Clean Air Act is a major success story by many measures. New passenger vehicles are about 99% cleaner for most tailpipe pollutants compared to the 1960s. The fuels themselves are much cleaner. Lead has been eliminated, and sulfur levels in the fuels are more than 90% lower than they were prior to regulation. Sulfur in the fuel, by the way, is bad because then you get sulfur dioxides in the exhaust, which are not technically regulated, but they're still pretty nasty. U.S. cities have improved vastly in air quality, despite increasing population over that period of time and increasing vehicle miles traveled, as we saw over that period of time. And the emission standards themselves have sparked technology innovation all across the industry. a prime example of that is the catalytic converter. But while there has been significant progress, regulators in the US and abroad continue to implement stronger standards every couple of years for vehicle pollution control because cities continue to get more dense. And in Europe, NOx and particulate matter are still of major concern because of all the diesel-powered vehicles over there. So it's a success story, and let's visualize that for a second. So on the left, we've got New York City in 1973. And on the right, we've got New York City in 2013. So still some room for improvement, as you can see, but a vast improvement over what it was in the early days before really the emission control was widely adopted. And looking at that more numerically, let's look at the historical standards. So these are the emission standards for NOx and volatile organic compounds, which is basically hydrocarbons. So these standards have gotten progressively more stringent as the decades have gone on, as the years have gone on, starting on the left part of the graph in the late 60s, early 70s, and then moving to the right towards present day. And they regulate them by how many grams, basically it's a weight that they can measure, how much comes out of the tailpipe per mile that's driven. So on the NOx standards, it was, unregulated cars were around 4 grams per mile, which is like unheard of by today's standards. It's a massive amount, actually. It doesn't sound very much, but multiplied by millions and millions of vehicles and millions of miles, it's a lot. But for both of these standards, it's a 99% reduction over time. So that is a success story for conventional vehicles, for sure. But what about electric vehicles? Well, there's no tailpipe, so there's no emissions from the vehicle itself. There's no air pollution coming out, and there's no carbon dioxide coming out. However, emissions can be released upstream from electricity generation. If grid electricity is coming from a coal-fired power plant, that releases significant sulfur and mercury into the air and into the water. Natural gas power plants are generally much cleaner, but it also emits some NOx emissions. As far as nuclear plants go, there is no air pollution or CO2, but the mining and refining of uranium requires significant energy, and there are other local environmental concerns as far as the mining, as well as incidents that could happen at power plants, as we've seen over the years. So those are the upstream components, but the big win, particularly with electric vehicles, zero emission vehicles, they have a very significant positive impact on local air quality, particularly when they're deployed in densely populated urban areas. Now, it's important to understand that lithium batteries do power modern electric vehicles, and there are local environmental concerns with the mining of lithium, cobalt, and nickel, which is all required. And the automakers, the national labs, there's an ongoing effort to make that process more environmentally friendly, but also to reduce the need for some of the rare earth items that are harder to find. So let's look next at greenhouse gas emissions, which they don't contribute to air pollution, but they do pose their own issues. So carbon dioxide, or CO2, is the product of complete combustion of a hydrocarbon fuel. The other thing that comes out is water vapor. This is a fundamental aspect of nature and cannot be changed. The more complete the combustion, the more carbon dioxide is released. Combustion has powered the Industrial Revolution, whether that's combusting wood or coal or petroleum, since the early 1800s. And that has resulted in significant anthropogenic or human-caused CO2 emissions in that time. Further, CO2 is a heat-trapping gas, and it causes incoming solar radiation to heat up the atmosphere and the oceans more quickly, the so-called greenhouse effect. It's worth noting that methane and nitrous oxide are also greenhouse gas emissions, but for these purposes, we're going to talk about CO2. So knowing all this, let's look at how much CO2 we've been putting into the air every year over time. So this plot from the Intergovernmental Panel on Climate Change shows global human-caused CO2 emissions basically since the mid-19th century. This is purely CO2 in gigatons per year. So in sort of tan, there's forestry and land use emissions, but the big one is gray, which is fossil fuel burning, the production of cement, and then flare gas from refining operations. So quite clearly, there's an upward trend of CO2 production. Okay, so the production is going up, but how has this affected the total amount of CO2 that just kind of resides in the atmosphere over time? Well, humans have been significantly altering the balance of CO2 in the atmosphere since the Industrial Revolution. This plot, which comes from Sustainable Energy Without the Hot Air, which was briefly mentioned at the beginning of the call, this tracks the concentration of carbon dioxide in the atmosphere over time, starting as early as around 1000 AD to the present. And the present, looked it up today, is 413 parts per million of CO2 in the atmosphere. And you can go to that website, co2.earth, and look it up any day you want. So the current level is 413. And the sort of acceptable level that a lot of experts agree on is about 350 parts per million. Now, the precise and exact effects of climate change are not yet known because we're living through history, but the general impact of CO2 being higher than acceptable levels, and therefore the global average temperature being higher than acceptable levels, are melting glaciers resulting in significant sea level rise, which impacts coastal communities, higher intensity weather events due to excess heat in the air and in the oceans. This can create increasingly violent hurricanes, tornadoes, droughts, wildfires, extreme cold events. And there's also a loss of biodiversity, particularly in the ocean. There's deaths of significant ocean species, such as coral reefs, due to increased temperature and increased carbon content in the water. So it's a problem. But how do we reduce CO2 emissions from vehicles? Well, we can improve conventional vehicle efficiency, the vehicle itself and the fuel production process, make that whole thing more energy efficient. We can work to transition vehicles to carbon neutral or even carbon positive fuel sources, such as renewably generated electricity or ethanol from non-corn sources. We can increase the adoption of electric vehicles, and we can increase usage of biofuels in different pathways getting to vehicles. So there's different things that we can do. So that touches on sort of the third of three. There was energy use, environmental pollution, and greenhouse gas emissions. So that's the big picture, but to sort of get a clearer understanding of how these are interrelated in different types of vehicles, let's look at an example. So let's look at sort of three different vehicles to understand the well-to-wheel impact of different types of passenger cars. So we'll do a conventional gasoline-powered car. We'll do a hybrid electric car, which is gasoline-powered. It has no plug, but it does have a battery. And then a pure electric vehicle that's powered only by grid electricity, charging a lithium battery. So how do we want to compare these three vehicles? Well, let's look at energy use, greenhouse gas emissions, and air pollution emissions, also known as regulated emissions. So to do this, I modeled this using Argonne's in-house tool, basically the mother of all spreadsheets, called the GREET model, Greenhouse Gases, Regulated Emissions, and Energy Use and Transportation model, to evaluate these. And this model is free to the public. Anybody can use it if they want to go look and make some comparisons. It's a highly powerful tool, and the group that manages it is sort of the life cycle fuel production group at Argonne. They are world experts. I used to work right down the hall from them. So let's look at this example. So a couple of assumptions I put into this sort of big spreadsheet, right? It was the year 2020, and they make assumptions based on the inputs. And the input was the year 2020, just all standard parameters. Let's look at just a regular passenger vehicle, regular average US national electricity mix for these three vehicles. So to compare energy consumption, and it spits out weird units of BTUs per mile, which is odd, but basically this is consumption, right? So lower is better. Let's reduce our consumption. And the orange bars represent downstream, or the vehicle. And then the blue represents upstream, or the production of the fuel. So when compared to a conventional, we've got the hybrid and the EV. The hybrid uses about 28% less energy, well to wheels. The electric vehicle is about 54% less energy. And on the greenhouse gas front, it's very much the same, a very similar story in terms of percent reduction. The hybrid uses about 28% less. And the electric vehicle, well, it's not zero, because that grid electricity that's coming from the upstream component is not quite carbon neutral yet. So it's still a significant component, and it's more significant than the upstream components of the conventional car or the hybrid. So this is kind of the problem area for electric vehicles. But even with that, it's 58% better as far as energy usage than a conventional vehicle. So that's energy, that's greenhouse gases. So what about air pollution? Well, hydrocarbons for a conventional vehicle plotted alongside the other two, it's a similar story. Hybrid is about 26% better. Electric vehicle is about 94% better. There is no tailpipe, so there are no hydrocarbon emissions from the downstream of an electric vehicle. Very similar story for carbon monoxide, although a hybrid is not much better than a conventional vehicle here, but electric vehicle is 98% better. There is no carbon monoxide coming out of the vehicle. Nitrogen oxides, it's not quite as much of a win, but that's because of, again, the electricity that's being used to power the vehicle. So it's still significantly better, but it's not perfect. But what's most important is that the vehicle itself is not producing any emissions. So again, if you have thousands of these in an urban environment, the sum total of those will have a huge effect on air quality over time. So electric vehicles are better, but they're definitely not perfect. But what's cool about them is that they will continue to get cleaner over time as the ways in which we generate electricity become cleaner. So in that regard, let's take a look at some positive trends. So this plot, taken from the Energy Information Agency, EIA, this shows electricity generation over time, up top here, from 1976 to about the present. And then down below here, it shows carbon emissions from electricity generation over time. So generally, electricity generation is kind of going up over time, and then it's leveled out a little bit here. And the CO2 emissions have generally gone up in that time until about 2008, and they've been gradually declining. So our generation is staying about flat, but every year our CO2 emissions are going down from grid electricity. Well, why is that? Well, let's look at where that electricity is coming from. We've got coal, natural gas, nuclear, hydro, renewables such as wind or solar, and then petroleum. And from the period of about 2005 to 2016, coal has seen a pretty significant drop as far as the percent of our total electricity. So in 2005, we got half of our electricity from coal. In 2016, it was a third. So that's a massive drop in 10 years. Natural gas has gone up significantly in that time. Natural gas is not perfect, but it is considerably better than coal. Nuclear has remained about flat. Hydro has remained about flat. Renewables are seeing a significant rise in that time. So obviously, depending on where the electricity comes from, depends on how much CO2 is going to result from it. But generally speaking, hopefully this kind of conveys the bigger picture of comparing a conventional vehicle to the sort of the opposite end of the spectrum of an electric vehicle, and what are the overall factors that are playing into how does the vehicle impact the environment, the energy usage, and climate change. So that kind of sums up what I had to say. I do include some pretty helpful resources in a couple of slides here, and I can find a way to provide the slide deck itself if anybody's interested, so you can actually click these links. You don't have to type them in yourself. But this is kind of where some of the data came from, and then there's some other resources that you can kind of go crazy in learning more. Stuff on batteries, historical vehicle miles traveled, energy use in transportation. And this is specifically the group I used to work in full-time at Argonne that generated a lot of the data for that electric vehicle study that I referenced earlier. So that is generally what I have to present. Hopefully it kind of presents the overall picture of how vehicles impact the environment and how some vehicles are better than others and how we're generally moving in a better direction and kind of have been for some time. So if there are any questions, I will be happy to answer them.
Patrick, thank you very much. Very interesting. This is Pete Suttmeyer up on Beatty Road. I had two questions, or interrelated questions. One, you mentioned very briefly at the outset about the hydrogen option. And I wonder, maybe it's not something you've looked at in great detail, but I wondered if you could reflect a little bit about that. And in a way, I asked that question because I keep wondering about some of the overall life cycle costs and problems with electric vehicles. Disposal of batteries, for instance, is one thing that comes along. But even when you think about the upstream requirements, and you think about where all the electricity would come from for a massive fleet of electric vehicles, it's hard to see that that could come from renewables at the moment. So I guess the two questions are that latter point, and then secondly about the hydrogen economy. Thank you.
Sure, good question. I actually had a half a slide in here that addressed hydrogen, but I kind of hid it at the last minute. Yeah, it's interesting. Hydrogen, there's hydrogen from the technical standpoint, and then there's hydrogen from the sort of political appetite standpoint. And the political, the winds of political change seem to determine whether or not hydrogen is in the current conversation, right? So on the technical side, there are pretty significant current challenges of lack of fueling infrastructure. There's storing it. There's challenges to storing gaseous hydrogen. There's challenges to storing liquid hydrogen. And then there's the kind of efficiency question, because hydrogen is used on board to generate electricity. And so the thinking is, well, why not just have an electric car? And, in a perfect world, you plug that into solar energy and there you go. So those are sort of current technical challenges, and they are real challenges. The joke in the industry is hydrogen is the fuel of the future, and it always will be. That said, if the storage infrastructure, basically, if those two are solved, then there's certainly a huge benefit to hydrogen because it's the most ubiquitous element. For the time being, electric vehicles are much more practical because the electric motor problem is well solved and the battery problem is sort of getting solved before our very eyes. Now, as far as batteries, there's certainly a concern with end of life, what happens to them. And all of the manufacturers have worked to improve the recyclability of them. I don't really have a figure as to what it is today, but all I know is that that's something that they constantly work on. So there could be a hydrogen component significantly in the future. I mean, it's kind of a niche right now in smaller markets like in California, and I think there's some hydrogen Hondas that are in England. Unfortunately, it's just the current tech. There's no like appetite to really devote huge resources right now to solving the technical challenges. Maybe that's because hydrogen is off and on sort of a hot button issue. And honestly, though, I think it's because we've seen such huge innovation in electric vehicles that the appetite for hydrogen is not very savage right now. So hopefully that answered your questions.
I have, are all electric vehicles equal? Are there some that are manufactured that are better than others in terms of energy usage and efficiency?
To my knowledge, there's not like a vast gulf between the manufacturers. It seems like when any given auto manufacturer takes it upon themselves to create, a green vehicle, they seem to be aware that people take into account more than just, the miles per gallon number. So like, Toyota uses certain, I think Tesla started using, like vegan leather and things like that. So as far as comparing one to the other, I don't have any data that would suggest there's a huge difference. I think it's really more a difference in how far do you want to go, how fast do you want to accelerate, and how much space do you want to have in the vehicle. But as far as production methods, I don't have any data to suggest that it's a significant difference from one company to another.
Okay.
I have one other question. As we look to more sustainable energy generation, one of the questions is storage. Can you comment on how electric vehicles may represent a distributed energy storage opportunity?
Yeah, there's a whole group at Argonne that works on, electric vehicle integration into a smart grid. So the first thing that has to happen is our grid has to be sort of vastly revamped, not only structurally, but also to include the communication protocol and sort of the controls to bring in two-way communication, two-way power flow from the grid to the electric car or from the electric car to the grid. Certainly having a field of or a fleet of electric vehicles out there at any given moment presents an opportunity to optimize the grid. I don't have the technical expertise to comment on the current status of that, but generally batteries themselves have a massive ability to not only enable renewables by storing that energy, but also I highly recommend anybody who's interested to look up the Hornsdale Power Reserve in Australia. This is, I think, the world's largest battery that was put into service, I think, in 2016 when parts of Australia were experiencing these huge rolling blackouts and the cost of electricity was enormous, and power plants were, going offline and coming online. And Tesla put this battery together in about 90 days and commissioned it. And just about overnight, they saw a massive impact because the battery could respond instantaneously and provide not only huge power to prevent a system from having to come online, but it could respond so fast to changes in the grid that and I'm not an expert on the economics here, but by being attached to the grid, it enabled the prices to just I think be chopped by about 60%, because it helps sort of balance out the overall grid. It's a really interesting story, and it was a bigger success than anybody was sort of anticipating. And it saved like tens of millions of dollars over, I think, the course of a year. So I think the potential for batteries themselves to have an impact for renewable adoption, as well as sort of grid stability and economics is pretty big, whether they be in cars or, just a stationary installation. But if you just search, like, I think it's, Tesla Australia battery, there's some really interesting articles that kind of look at the impact, the financial impact of it, and the environmental impact of it.
Thank you.
Patrick, I'm wondering, what is Argonne Labs and why are they involved in this issue? Who are they?
So Argonne was actually born out of the Manhattan Project in 1942. It was the location of the first nuclear chain reaction under the bleachers of the football stadium at UChicago. So Argonne was born out of that, and they've obviously evolved into different things over the years, but they are a basic sciences laboratory as well as an applied science laboratory on the outskirts of Chicago. And Argonne has a significant transportation department that looks at the cars, that looks at the fuels. So all the national laboratories do research, for the benefit of everybody, for the benefit of the public, to research what's possible scientifically, to help with standards development as, technology evolves. And they do research and publications that gets, kind of sent up the chain to DOE for policy-making decisions. And Argonne's got kind of a very diverse portfolio. I mean, there's biology research there. They've got a particle accelerator. There's transportation. There's counterintelligence division. There's physics. So it's kind of a wide-ranging array of science work that they do there. And the overall mission of the national labs is to support the Department of Energy's various initiatives, whether it's around nuclear energy, nuclear weapons proliferation, energy security, energy sustainability. They don't really get into environment. That's EPA's territory. But there's always some sort of energy bent to any work that's done at a national lab.
I was curious if you knew how compressed natural gas compares to, say, gas or electric vehicles, because I know in Europe they seem to use CNG. Yeah,
CNG definitely has it has some benefits, particularly for fleet vehicles, as long as the infrastructure is there. CNG is cleaner on the tailpipe emissions front, and it's a more efficient process, from start to finish than refining petroleum into gasoline. The challenge there is infrastructure, and then getting the automakers to produce CNG vehicles. So there kind of has to be a consumer appetite, as well as the policy put forth to put infrastructure in place. And they are certainly more ubiquitous in Europe. Compared to an electric vehicle, it's not as much of an efficiency win or an emissions win, but it's less, getting a conventional engine to run on CNG is much less of a technological feat than, designing a ground up electric vehicle. So it's part of the portfolio, I'd say.
Okay. And you had made mention of lithium, which is actually an extremely rare element.
Yeah.
But I'm also aware that there is some research. I've seen some of the research going on into like other more abundant elements like sodium and sodium ion and I'm trying to think of like potassium. They're like playing around with those as well. for the batteries. I don't
Yeah.
think that they're necessarily as efficient for the battery, but at least you have less need for the rare earth elements and less pollution.
Right. Yeah, absolutely. That research is being done by automakers as well as national labs. Because
And at the university that I work at as well.
oh yeah, yeah, it's a great point, because if we have wars fought over oil, what's to say we're not going to have wars fought over a precious resource like lithium if our whole
Right.
transportation sector is reliant on it. So yeah, there's definitely efforts to reduce the need for rare earth metals. And it wouldn't surprise me if Tesla was one of the first ones to innovate on that. It's interesting how technology moves in at different paces. So the Chevrolet Volt, which came out in 2010, which was like a huge deal at the time, it was the first plug-in hybrid ever put into mass production. The technology for that battery was proven in the lab at Argonne in 1990. So that took quite a lot of time for it to get to market. But then from there, to see what has happened with electric vehicles, whether it's Tesla or Nissan or almost all of them, all automakers are making them now, from 2010 until now, it's been a huge explosion in number of them, and the batteries themselves have gotten just vastly better in only 10 years. So it's really, it's kind of an example of how technology can accelerate on itself. And I think we have to assume that finding better ways of building batteries that don't require as much lithium is going to be part of that process.
Patrick, I have one other question. Just on a side, you said that cement affects CO2 emissions. It's one of the things you listed. How is that? Why is cement different?
I don't know the exact process, but I do know that the creation of cement creates an awful lot of carbon dioxide. I don't know the exact details of the process, though.
Okay.
And I think, I'm not sure if asphalt falls under the same category, but certainly cement. And I think that there are green building initiatives, like LEED certification. I want to say that there is a component of, what the building is made of and what's the carbon, the carbon impact of the building materials themselves.
Well, if there are no more questions, I want to thank you for bringing this to our attention. And for really, it's so well researched, and I had never thought about the upstream and the downstream and the making of the car and of all of that. It's very interesting. It makes me rethink what I drive.
Good. Hopefully folks enjoyed it.
Yeah.
Patrick, it was wonderful. I really liked it.
Thank you.
Good. Thanks.
Yes, thank you very much.
And I will say, if you've not driven a powerful electric car, there's something that I learned in grad school when we built a plug-in hybrid car for this grad school project. And there's something called the electric smile, because once you drive one, there's kind of nothing else like it. So if you get a chance to test drive one, if nothing else, you'll have a lot of fun. So give it a shot.